In the last module, we introduced the idea of entropy. As you probably know, the second law of thermodynamics states that in any process, the change in entropy of the system is always greater than or equal to zero. In other words, the entropy of the universe is always increasing, and this is just a statement that the universe is evolving into its most probable configuration. Now, this is true for any system in equilibrium with its environment. It is not true for a system out of equilibrium with its environment. Glaring examples of this are at the most complex level, living organisms. These evolve greater complexity with time in apparent violation of the second law of thermodynamics, but of course we are not in thermal equilibrium with our environment. A fridge is a much simpler example. In a fridge, heat is pumped from a cold area to a hotter area, apparently in violation of the second law of thermodynamics, but actually the second law of thermodynamics has nothing to do with the fridge alone, only with the total environment of fridge plus the universe in which it sits. So let us turn then to this Boltzmann distribution, the single most important quantity that we will introduce in this chapter. The Boltzmann distribution addresses the question of if one has a system that can occupy certain energy states, E1, E2, E3, and so on, what is that distribution of population of those states going to be if the system is in thermal equilibrium with its environment? So what we are doing here is actually rather complicated. We're taking a look at our system. For example, the velocity of molecules in a gas, or the distribution of spin states of a magnet in a magnetic field, and we are ignoring the fact that the system, the molecules in a gas or the magnets, the magnetic elements inside a magnet, are exchanging energy all the time with atoms and molecules in their environment to keep them in thermal equilibrium. We're replacing all of this complexity by one parameter, the temperature T, and asking what the distribution is in that isolated part that we are calling the system and we're trying to solve the physics of. So where does the Boltzmann distribution come from? Well, it's relatively easy to see how it must take the form that it does. If we ask what is the probability that system 1 is at energy E1, and simultaneously system 2 is at energy E2, then for classical probabilities, we know that the probability for these to be simultaneously true must be the product of the individual probabilities. However, if we ask what the total energy of the system is, this is the total probability, energy is a conserved extrinsic quantity, so when we add two systems together, we add their energies together. So we're looking for a mathematical function in which the argument of the product of the functions is the sum of the energies. So this is true of exponentials, because if I take the exponential of E1 and I multiply it by the exponential of E2, then I will get the exponential of E1 plus E2. So a system whose total energy is E1 plus E2 and whose probability of occurring is the product of the individual probabilities. Now, this isn't going to work for our distribution because it says that two things are wrong with it. First of all, it says that the probability grows exponentially with energy, and we certainly don't want that to be the case, so let's put a minus sign in here. And secondly, our exponential has to be dimensionless, and we expect that the energy of a system will scale with temperature. So let us then divide by temperature and introduce an arbitrary scaling constant k. So now we have our distribution. This distribution, the probability of being in an energy E at a temperature T for a system in thermal equilibrium with its environment is given by E to the minus E, the energy, over a constant times temperature, is the Boltzmann distribution. And for this distribution, the Boltzmann constant, i.e. the constant that relates the energy in joules to the temperature in degrees Kelvin, is given by 1.38 times 10 to the minus 23 joules per degree Kelvin. The Boltzmann distribution is plotted for various values of this parameter kT or beta on this plot here. For the chemists amongst you, the equivalent of Boltzmann's constant in calories per mole is approximately 600 calories per mole. So I just showed you the Boltzmann distribution without normalizing it. And so let us now look at the problem of normalizing it. And I have on this slide the definition of the normalized distribution. The probability of a system being in the rth state of energy R, ER, is proportional to E to the minus ER over KT. And the normalizing constant here, which I've called 1 over Z, is a very important quantity. It is just the sum of the probabilities that the system is in any state, so that when I divide by this sum, I get the probabilities that will sum to unity if we add them all up. This quantity Z is called the partition function. In addition to normalizing the Boltzmann distribution, it is the function from which thermodynamic quantities can be evaluated from a microscopic model, because in working out Z, we have to enumerate every state of the system and then weight the probability of that occurring. So we have therefore described microscopically every possible state of the system. So we will see more of partition functions in the future. Let me end with Boltzmann's definition of entropy. Boltzmann's definition, written on his grave, is that the entropy of a system, given by this Boltzmann constant, times the logarithm of the number of ways that the rth state can be achieved. So, to give a very trivial illustration of this, if I have a pile of 3 bricks and I want to achieve a final state 3 bricks high, there's one and only one way of doing this. And so the entropy of the system, the statistical weight is 1, the logarithm of that is 0, and the entropy of the system is 0. On the other hand, if I can put the bricks, I ask for a state in which I have just 1 brick height, I can do this by a number of combinations of laying the 3 bricks in any order, and the entropy will be higher. The Boltzmann definition allows for the entropy to be an additive quantity, just like energy, so it's a good extrinsic thermodynamic property of a system. The number of arrangements, however, that a system can take on if one takes 2 systems, each with a statistical weight omega, becomes multiplicative. So this definition of entropy mirrors Boltzmann's probability distribution and has the right thermodynamic properties for both entropy and statistical weight.